So what's up, guys? Welcome to Venom Prunov Academy, and in our today's video we are going to focus on irrational numbers. So what are irrational numbers? Irrational numbers are simply numbers that cannot be expressed as a fraction, and the decimal part of these numbers is simply going to be non-reoccurring and non-terminating. In short, they're endless. So when you think of irrational numbers, you think of numbers like pi. You're going to think of numbers like pi. You're going to think of numbers like E, the Euler's number. You're going to think of phi, which is the golden ratio. You're going to think of the root of 2. Not only the root of 2, but the root of each and every number that is not a perfect square number. Okay? It's going to give you a rational number. And you find that the decimal part is going to be non-terminating and it's going to be non-reoccurring. So, for example, when you look at pi, you simply find that the value is going to be 3.142, and the numbers continue going. And when you look at, probably this should be a 5, and when you look at this, the Euler's number, you're going to get 4.1132, and the numbers, the digits continue going. When you look at phi, you're going to get 1.6180, and the digits continue going. They are not reoccurring. Okay, when you look at the root of 2, you're going to get 1.4142, and the digits continue going. Okay, but remember, in terms of the roots, it's the root of each and every non-perfect square number that you get is going to give you an irrational number. Okay, things like 10, when you put 7, all these are going to give you irrational numbers. Okay, and we remember that these numbers cannot be expressed as a fraction. And remember, just like the way it is in terms of science, we've got positive and negative. Whenever a number is not positive, then we know it probably should be negative, and if it's not negative, it should be positive. The same applies. If a number is not rational, then we know that it is irrational, and vice versa. Okay, but remember that both of these numbers belong, or both of these sets of numbers belong to a larger set of numbers which are real numbers. Okay, so in this video I want us to look at how we are going to prove to say these numbers are irrational. Okay, but if you should remember, these numbers are not so exotic. These numbers are not hard to find, because for at least every 2 rational numbers that you take into consideration, in between them you are likely to find at least one irrational number. Okay, so these numbers are everywhere. They're everywhere. I know we usually don't encounter them, or we usually don't take them into consideration on several occasions, but these numbers are everywhere because they exist. Okay, they exist between each and every 2 rational numbers that you take into consideration. You're going to find at least one irrational number, and I use the word at least to show that there can be one or more numbers existing between every 2 rational numbers that you take into consideration. But then, how are we going to prove that a certain number that we have is an irrational number? Remember, if a number is not rational, then it is irrational. Okay, that is the basic standard that you should commit to mind. So we are going to use a method that we call the contradictory method, or we are going to prove by contradiction. Why? Because we are going to make an assumption and suppose that a certain number or a certain given number is rational, and prove as though we are trying to find or to show that it is rational. But at the end, if it does not meet the criteria of rational numbers, where it can be expressed as a fraction a over b, and both a and b are members of integers, and b is not equal to 0, and both a and b are in the lowest terms, then we make a statement to say, since it does not meet the criteria of rational numbers, this number should be an irrational number. Okay, so let's suppose we've got the root of 2. Okay, and we want to show that this is an irrational number, because we know that it is an irrational number. Now we want to prove, or we want to show that it is an irrational number. Firstly, I would like you guys to remember a certain theorem. Okay, so this theorem, what it's simply going to tell us is, if a perfect square is divisible by a certain number, then the number that we used to obtain that perfect square is also going to be divisible by that same number. What does that mean? We know that perfect squares are simply numbers or values that we are going to obtain by multiplying a number by itself, okay, or by squaring a certain integer. So when you get 2 integers and you when you get one integer and you multiply it by itself and obtain a certain number, that number is going to be a perfect square. Numbers like 4, okay, when you get 2 and multiply it by itself, you get 4. When you get 3 and multiplied by itself, you get 9. When you get 4 and multiplied by itself, you get 16. When you get 5, what do you get? You get 25. When you get 6, you get 36. When you get 7, you get 49. And 8 gives you 64. 9 gives you 81. 10 gives you 100. So all these numbers that we've talked about are perfect squares. Why? Because we can simply get one integer and square it to get this number. So what this means is, let's say if x squared is divisible by a certain number, okay, or let's say by a certain letter v, then x is also divisible by v, okay. So what does this mean? If 9 is divisible by 3, then 3 is also divisible by 3. If 16 is divisible by 2, then 4 should also be divisible by 2. If 25 is divisible by 5, then 5 should also be divisible by 5 without giving a remainder. This is what this theorem is trying to tell us, okay? So we are going to regard this theorem, and let's put this theorem to memory as we solve this given question that we've been given. Okay, so let's assume we've got the root of 2, and remember we are proving by contradiction, so we are going to make an assumption. So suppose, let's say suppose the root of 2 is rational, then what should be true? If the root of 2 is rational, then it should be expressed as a fraction in the form of a over b, where a and b are members of integers, and b should not be equal to 0, and both a and b should be in their lowest terms, okay? This is the assumption that we make. Now, if you guys did your indices properly, then you realize that every time you've got a square root, so this is a square root, it's simply equal to 1 to the power 2, or 1 over 2 rather. So if you've got a number, let's say the square root of 2, it simply tells you you've got 2 to the power half, okay? So if that's the case, then we've got the root of 2 should be equal to a over b. What do we do to eradicate the half, or to deal with this root? We are going to multiply everything by 2, okay? So let's continue on the other paper. We are going to continue. So we ended here where we say this, then we multiply everything by 2, okay? So when we distribute the 2, because here it's more like we've got this, and this side we've got a over b. And remember, again, when you dealt with indices, this a over b squared is simply equal to a squared over b squared. If you've got a over b in brackets, then it's squared, then it's simply equal to a squared over b squared. So we are going to distribute. When we multiply 1 over 2 times 2, we simply get 1, which is simply 2 to the power 1, and 2 to the power 1 is 2, okay? Then this side, we are going to get a squared over b squared, okay? If that's the case, what do you do now? You cross multiply. So when you cross multiply this side, you get 2b squared should be equal to a squared, okay? When you obtain this, then you know that you can divide this side by 2, and this side you can divide by 2. What do you get? You get that b squared should be equal to a squared over 2, okay? Now, at this particular point, I would like to make a statement, or I would like to make a point. At that particular point, we realize one thing, okay? We realize that if we've got this statement, 2b squared should be equal to a squared, then we know that b squared, or rather a squared, can be divided by 2, just like what we have done here. We've divided a squared by what? By 2. So, since a squared, you make a statement, okay? So at this particular point, we can make a statement and say, since a squared is divisible by 2, why? Because we are dividing a squared by 2. Then a is also divisible by 2. Remember the theorem that we made? Yes, so this is why it comes in. So let's continue from here. We ended it at the point where we said b squared should be equal to a squared over 2. We just gave a statement to say if a squared is divisible by 2, then a is also divisible by 2. So what do? Choose another number, okay? Equate a to something. So let's say a should be equal to m, okay? And we say m, this number, this m should be a member of integers, right? Then what are we going to do? Then we are going to say b squared should be equal to, what is our a? Our a is 2m, so should be equal to 2m squared over 2. What do we get? B squared should be equal to, this is going to be, when you distribute, you get 4m squared, okay, over 2, right? So this side, what do you realize? You realize that you're going to have b squared should be equal to, when you divide this into this one, this into this 2, so you get 2m squared. And what does this tell you? You can find the value of m. In short, you can divide both sides by 2 if you wanted to. So you can simply put a statement and say, since b squared is divisible by what? By 2, it means B is also divisible by 2, right? Is also divisible by 2. Now, I want you to tell me something. If both of these numbers are divisible by 2, what does it mean? It means these numbers have got a common factor, right? So, remember the assumption that we made. We made an assumption to say the root of 2 is what? The root of 2 is rational. And we say for something to be rational, then it should be expressed as a fraction in the form of a over b, where b is not equal to 0, and both a and b are members of integers, and a and b are in their lowest form. In short, when we say their lowest form, we mean there shouldn't be any common factor between those two numbers. But from the theorems that we've made on both cases for a and b, we've realized that they both have a common factor, what? 2, which can go into these numbers. What does that do? It contradicts. So, since you make a statement, this is your final statement. Since both A and B are divisible by 2, this contradicts our assumption that the root of 2 is rational, existing in its lowest form. Okay? Existing in its lowest form. Hence, the root of 2 is irrational. Because remember what we said in the previous video, that for something to be regarded as rational, it should meet all the conditions, okay? All the 3 conditions, it should meet them. But this one does not meet one of the conditions. And if it does not meet one of the conditions, then we regard it as what? As irrational. But on this part, I simply don't want to limit you to use my words. Just know what you're trying to communicate to the person reading is that both A and B are divisible by 2, or they've got a common factor 2. And if that's the case, then this contradicts, or it does not respect or obey our earlier assumption that we made, that 2 is in its lowest form and it can be expressed as a fraction. And if it does that, then we know that the root of 2 is not what? Is not rational. So hence what? Hence proven or shown. Okay? If they asked you to prove or to show, then you've shown. Okay? So this is how you're going to be proving these rational numbers. But sometimes you're going to have, let me just give another example. Sometimes let's say you're going to have a question like the root of 2, okay? The root of 2, let me just say, okay, let me say 4 plus the root of 2, okay? And you know that this is irrational and they're asking you to prove. So you simply make the same assumption and equate this to a over b. When you equate this to a over b, you cross multiply. So you're going to have b multiplied by 4 plus the root of 2 should be equal to a. When you distribute, you get 4b plus b, the root of 2 should be equal to a. Then what you realize is you're going to do what? To shift or to shift this 4b to take it to the other side, okay? What are you going to have? You're going to have b root of 2 should be equal to a minus 4b. Then you divide both sides by b, okay? Now, what do you realize? You realize that you've got 2 different things this side, okay? b. So you can, if you want, you can reduce it as a over b minus 4, okay? Because this is common this side. You can have 4 over b, then cancel out this. Okay, now you've seen that on the left side, yeah, you've got the root of 2, which is irrational, but on the right side we've got something, an expression that is rational. So since what you have on both sides is different, you conclude that this entire thing is what? Is irrational. Remember, for you to use this equal sign, what you're trying to communicate is what is on this side and on the other side are equal, okay? But according to what we found in this example, we can prove that the root of 2 is simply not equal to a over b minus 4. This side we've got an irrational number, but this side we've got a rational number. So this means the root of 4 plus the root of 2 is what? Is irrational. Hence shown. So you're going to encounter most of these questions, or questions asking you to prove whether a certain number is going to be an irrational number or what. But then you just follow the same procedure, the same theorem, of course, based on the root that you are using. When you're equating m to a certain number, not only m, you can use any letter. When you're equating, let's say a, at the point where we equated a to 2m, if you are proving that the root of 3 is irrational, then you are going to equate a to 3m, okay? If you are proving that it's the root of 7 that is irrational, then you are going to equate a to 7m, okay? That's what I wanted. And remember that m should be any member, or should be a member of the set of integers, okay? So now, this is how we prove that certain numbers are irrational numbers, okay? And in the next video, I'm simply going to show you how we find the irrational numbers existing between 2 rational numbers, and also the irrational numbers existing between irrational numbers. So thank you for tuning in, and please don't forget to subscribe, to like, to comment, and to share this video. Supposedly you've got any need or anything that you want me to clarify on, please feel free to comment and put it in the comment section, and I'll quickly respond to that. Thank you very much.